Okay, so I woke up in the middle of the night, little picture in my head. Thought I'd share it with you. I'm going to try to keep each of these videos shorter, hit the major point, and then if I get on a ramble, I'll just end the video and go. I'll pick up from here in part 2, part 3, so on and so forth, because this just scratches the surface of where we might go with it. Okay, so if I ask somebody in the back of the room to read me number 2, they might say parentheses x minus 5 end of parentheses squared. All right, so we got something in front of us now. But if I were to ask someone to explain to me what this is asking me to do, I think trying to say that as succinctly as possible would be nice. And I think when I look at that, I see that this thing, I'll call it, measures. That's what we do in math. We measure things. Measures squared change from 5. Not simple enough sentence. There's a lot going on there. And so we have rulers in math. We generally start with the letter X, which is a horizontal ruler, which measures from 0. We are now going to measure from 5. We're going to measure from here. What are we going to measure? Squared change from 5. And I want you to draw the picture of that squared change from 5 to the number 8. And you pause the video, draw the picture. So I'm going to erase the x-axis and say, you're right here. Would you please draw the squared change from 5 to the number 8? Pause the video, work with it as long as you want. When you're done, unpause, because I'm just going to keep talking now. Well, the first thing you'd have to do is you have to get to the number 8. Okay, there's 8. Well, what did I just draw? Looks like I just drew a line. No, I think that's a one-dimensional picture. You need to make it a two-dimensional picture. And I think I know what that distance is. It's 3, which means this altitude is 3, and it looks like I just generated a measurement. I can tabulate this, and that measurement produced the number 9. Now, we're not going to leave it like that. We're going to go to René Descartes and thank him for his contribution to the field of mathematics. And we're going to start at 5. We're going to go to 8. And we're going to say, hey, you did square change from 5 and you went to 8. Well, you just changed by 9 units. And then you read it over here, of course, because we don't really draw that bar, but that's what our brain is doing. Well, what if we wanted to measure square change from 7? Well, I guess we got to find 7. You got to look at the square change. And that one's smaller. That one's 4. But we don't draw the box. We just draw we don't even draw the line. We just, say, well, that's 4. And if we went to 6, well, that's 1. And we start to see this trajectory. How nice. Okay. Most textbooks would look at this and they would, explain it to you as, well, this is the parent function and you've shifted 5 units to the right. Well, I'm not sure that description is the best initial one, because that felt like a video game. It felt like the old Mario Brothers or the old ping pong thing. I'm pretty old here. Computers have come a long way. A lot of games are a little more interesting than the ping pong game that first came out. Right. And the first graphing functions came out and they'd go dot, dot, dot. It took forever, but it would, show a picture of that graph. And I suppose we're being discriminatory in the positive direction. We probably should move to the negative. Well, any value I put in less than 5 creates a negative sign change there. There's a sign change in 5. That's important. We're going to talk about that in great detail later. So 4 is a 1v1. We don't draw the square, but the dimension is a 1. So we can, I suppose, use the bar graph. 1 over here was a little lower symmetry. So there's 1. And if you did 3 from 5 to 3 is a 2v2. I think you got the idea here. That's 4. And if we get to 2, well, 5 to 2 gets me the same answer, because from 5 to 2 is -3, but -3 times -3 gets us that 9 units of change. Well, that's nice, because now I got a little feeling for that graph from a little different perspective, and shifting in perspective I like. I don't know if I'm running with the shift perspective. I always felt like this graphing transformation was like the song YMCA. Teachers will appreciate this. YMCA. Shifting vertically, horizontally, and I don't know the squeezing it. I don't even know the language anymore because I haven't used that language since 1993. I've been playing with shapes. Part 2, we're going to play with shapes a whole lot more. Yeah, all right. But what happens if I didn't want to go through 8, 9? Well, I guess, maybe I want to go through, maybe I want to double this. So maybe I want to, double that. That looks like it's doubled. Then I'm not going up 9. I'm going up 18. And I guess I got to show doubling with a little number there. And the number 2 appears to be 18 divided by 9. Because if I went over 3 and squared it, I should get 9 units of change. But if I want 18 and I got to double it, I can see that 2, that ratio of change by 18 over 9. And that takes me to 18. Well, what if I wanted to just go to 17? Maybe I don't want 18. Well, I guess I just change that. Looks like it gets the job done. Let's see if it does. Let's put what number? 8. Let's put 8 in here. Well, that gets me 9 units. I don't want 9 units. I want 17. Yeah, 8 minus 5 is 3. 3 squared is 9. And I get 17 units of change. And that's what you're trying to learn how to do. You won't find it in the textbooks, unfortunately, but hopefully it'll go mainstream at some point. So let's go 4, 7, and let's say you get 9 and 20. Right? So what's that equation? Well, we're measuring square. We see the signature of the squaring process. So I would hope you'd start with x minus 4 squared, but we're not starting from 0 anymore. So we got an initial condition here. 7 units are already present. And what are we trying to get to? To 20. Well, I just learned something here. From 7 to 20 is 13 units of change. But if from 4 to 9, I know what the quadratic change to 4 to 9 is now. Oh, 4 to 9, 5. Oh, it's 25. I don't want 25 units of change. I don't want 25 units of change. I'm looking for 13. I guess I erased this. And that's what you're trying to learn to do in class. And some of you are getting success with that now mechanically. Thought we'd draw a little bit of a picture there to augment your understanding of this. Give it a little bit of a bump. Right? Maybe that just did, maybe it didn't. My hope was that it did. We could do cubics too, couldn't we? We could do cubics. Let's do a quick cubic change, just so you get an understanding what, cubics look like. But am I starting to ramble? Maybe. I don't know. Yeah, I think I'm starting to ramble. So is there anything else I want to say here? Yeah, there's one last thing. So 0, 1v1, 1, 2, 1, 4, 3. Last thing I'll say, and then I'll go to cubics in part 2. Somebody wants to look at that. All right, did I bring my box with me? No. Oh, what a shame. I brought it downstairs. Well, I'm not gonna do this again. But if you look at this from the standpoint of, I don't need the box for this one. I'm doing just the square. Okay, I'm in good shape. So how do we get from 4 units to 9 units? Well, let's color this in. Let's call that. You know, it's a solid. Well, I got to get a little bit bigger dimension. Right? It's just got to get a little bigger. And then I get a new strip of area. Yeah. That's what a derivative is in calculus. I just went from 2, an area of 4. I just increased by, let's say, the smallest amount. And if I square that, I get 4.004001. Now remember, this is a 2 by 2, or an x times x. And I just did a 2 once and another 2 twice, basically. That's what I did. And that's that change is twice that number. And if I kept doing this and doing this and doing this, I'd eventually get to a 3 by 3 size. And in calculus, what I just did was what is called integration. This is the side length of the square. I'm taking 2 sides. And on dx is really the 0.001. It's just a small change in x. And if I went from 2 to 3, then I'm going from x squared is what produces that change, from 2 to 3. And I'm going from 9 units to 4, or from 4 to 9. If I put 3 into x squared, I get 9 units. If I put 2 into x squared, I get 4. And that's what you would do in calculus. Now, let's look at this one. How is 3 by 3 changing? Well, 3 squared is 9. And 3, let's do a big one. You can check this on a calculator. Let's do 3, get you 9. Let's do 3.01. 1, 2, 3, 4, 5, 6 decimal places gets me 9.1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. Check it on a calculator. What's the change? Well, the change from 9 to this, we don't care about that. That's really all about the cusp. Ignore it. The change is right there. That's the change in y. What's the change in x? 0.0, there's a point there. 0.00001. Well, that's a 6-to-1 ratio change, which means that at 3, 9, we'll put it right here. I'm going up at 6-to-1, twice that. At 2, I'm going up at 4-to-1, twice the 2. At 1, I'm going up at 2-to-1. I'm not drawing these well, but maybe you can start to see that process from the standpoints of rates of change. And I told you that right now because, for one thing, you're probably not going to hear that discussion in your calculus class. I never drew these pictures for 3 years and I took 4 calculus classes. I'm really trying hard to learn what I'm doing as a profession. And it dawned on me after 3 years that this was all about the geometry, the change in geometry. And it helped me understand what I was looking at. And so I want to plant that seed right now, because if the first time you hear this is your senior year when you take a calculus class, I don't think there's enough time to process what you're looking at. If you don't have a picture in your head of what's going on, it's harder to grasp. All right, so we're going to try to get pictures of everything here, the initial origins of this discipline. And if you have a picture in your head, oh, you're going to own this stuff. All right, that's part 1. I'm going to talk about cubics. It's very rich geometrically. Bye.